well, I'm very happy to be here, and it's very kind of the organizers to think of me to invite me to speak here. So I don't give one of these overview talks that tells you everything there is to know about harmonic analysis. I picked this one thing, and my goal is to show you a little bit how it interacts with PDE and with probability, and at the same time to put light on a new result that I did recently with two different proofs. So if at any moment in time you don't hear me, I can either turn my head or speak louder. It's no problem. Just let me know. So I have been made aware of an operator that is convolution by 1 over n in the integers a while ago. And the fact that LP norms of this operator are not known. And when I saw the operator, I figured, well, that's going to be an easy exercise. And it took me about 2 years to understand that it was not an easy exercise at all, and I still don't know how to do it. But this is the work that came out of this kind of line of research. And I would like to show some sort of beautiful interpretation of singular integrals and what they are, hopefully in a way so that everyone can understand. So in this lecture, it is a talk of very many second chances. So if at any time you don't understand anything, it starts over all the time. So it shouldn't be a dreadful 50 minutes of just sitting here. So my talk, it's about sharp LP estimates. So generally about sharp LP estimates of certain singular integral operators. So, but first I'm gonna tell you what those things are. So I'm interested in LP estimates. So LP functions are those functions of which you can raise their magnitude to the pth power for some p between 1 and infinity, integrated and take the pth norm. So this is a norm in those integral functions. Usually we think of Lebesgue measure, but you don't have to worry about any kind of crazy function here. So this is the norms we're dealing with. And then there's an operation, a basic operation in harmonic analysis, or in many fields, which is a convolution by a kernel. So this means you take locally averages of the function f, and you integrate them again. So we will see in a second what that is. So if you integrate with a function that is integrable with power 1, namely in L1, then you can fairly trivially estimate this. I'm pretty sure you've done all this exercise in your real analysis class. So it's just pretty easy to find like functions k that are not in L1. So one of them is 1 over x on the real line. It's not in L1 because you integrate it and you fail. And 1 over z squared in the complex plane is not in L1, and xi divided by norm of x to the n plus 1 is not in L1. So those are important operators, and they have important names, namely Hilbert transform, Beurling-Ahlfors operator, and Riesz transform. So by their important names, you might guess that they are important operators. So even though it's not completely trivial, one can show that all such operators and operators that are very much like it, they are bounded in LP for p between 1 and infinity. So this means that there is an absolute constant Cp, so that if you apply the operator to a function, you measure its LP norm. You can control this uniformly, independently of f, by the constant Cp by the LP norm of f. So now you might wonder, if you run through all such functions that are in LP, what is the best possible constant Cp that you can put there so that it still works for all functions?
Is that constant uniform over dimension?
Right now I haven't even specified the operator. So T is supposed to be, just think of a specific operator. We're not looking for a universal constant for all operators. So usually you're singling out one operator, and you say, for this operator I would like to know. Like to know the Cp. So, okay, so here's an example of a convolution. So this is the one that is convolution by 1 over z squared. This is the Beurling-Ahlfors transform. So that integral is a convolution integral where you take f of w, convolve it against 1 over w squared. Convolution means that you're looking at the difference on the bottom, and then you integrate this. So this has to be defined correctly. So this is called a principal value integral. So you basically do your best for functions that you can integrate that. Usually you try to stay away with f from the singularity so that you don't ever hit when the denominator is 0, and that will give you one way to look at this integral. So we do not know the LP norm of this operator. So it basically is a long-standing conjecture that the exact LP norm of this operator should be p minus 1 for large p and 1 over p minus 1 for small p. Now I'm pretty sure the best constant right now is 1.4, but it may have been improved a little bit. So it's 1.4 times the conjectured norm. And the best deterministic proof for this estimate is 2 times worse than the conjectured estimate. And so this operator t, it has a real and an imaginary part. And you can look at its real part alone, which should, in theory, have a smaller norm. The trouble is it doesn't have a smaller norm. So the real part of this operator already has norm p minus 1 or 1 over p minus 1. So essentially all the things that are known, they are really not very nice because they are doing some operations that are splitting this operator into pieces that they shouldn't. So we just don't understand this operator. So why would you care about this? Well, either you just care about the operator or you care about PDE. And then you can look at a natural form of a PDE. So you've probably all learned that the d bar derivatives of analytic functions are 0. So now if you build in a defect and you make a PDE in the complex plane, where you're now no longer saying that the d bar derivative of f should be 0, but you're making an equation to say that df equals mu d bar f, where mu is a small L infinity function. Now it's not super elegant, I'm sort of looking at anti-analytic here instead of analytic, but we're trying to control essentially we're trying to make a relation between d and d bar derivatives by a small L infinity norm. So this is a very famous equation called the Beltrami equation. So for such type of equations, you often get a trivial solution, which you can just write down with the help of singular integrals. So this trivial solution will have mapping properties that are very close to those of analytic functions. So you probably remember that analytic functions, they map small disks to small disks. So this kind of solution will send small disks to small ellipses. And the L infinity norm of the function mu will give you the eccentricity of those ellipses. So now, this operator here, identity minus mu times t, is really tied to this equation because t, the Beurling-Ahlfors transform, which is convolution by 1 over z squared, has a very special property. If you plug in a d derivative of f, it spits out a d bar derivative of f. So because of this situation here with a d bar, and because t applied to df gives you d bar, this operator identity minus mu t is intimately tied to this Beltrami equation. So, and in PDE, very many times, aside from your trivial solution that has very nice properties that you can just write down, you might wonder about all solutions. And then you will ask about what kind of regularity do these solutions have, depending on all the parameters involved in the equation. So what is the minimal requirement of the type of a Sobolev class, which guarantees that any solution where we know the L infinity control of this mu, the eccentricity of the ellipses, self-improves to be in a much nicer class, which makes that solution automatically continuous. So we are wondering what kind of a priori regularity you need to assume so that this a priori regularity, which is a very crappy regularity, will automatically give you a very nice regularity. So those are typical questions in PDE. So now, if your k is always less than 1, so the bigger this k is, the smaller the range will get. Okay, so this p moves really close to 2, and when it's equal to 2, there is no more self-improvement happening. So the range of which you self-improve really depends on the L infinity norm of this mu, And it's a very famous theorem with the strict inequality by Astala, Ivanits, and Saxman that the strict inequality holds. And it was a long open question. Can you do the 1 plus k? And with the reduction that they had done to weighted estimates, we were able to prove this with my thesis advisor in 2000. And it's actually a very easy proof. Once you have the reduction done by those guys. And now I want to show you how this relates to weighted estimates in LP. So if you can trust me that this operator, its injectivity and invertibility relate to the question of self-improvement, which is not very hard to show, but let's take it for granted right now. So let's suppose we knew what the LP estimate of the Beurling-Ahlfors is. So then we can do an extremely wasteful, almost crazy estimate to recover this famous result. So we're looking at the inverse of this identity minus mu t, and we're trying to see if it's invertible in LP. So we're trying to estimate the LP norm and see if it's finite. So this is like of the form 1 over 1 minus a. So you do a geometric series, and it'll just give you mu times t, which is what's written here, to the power of n for all positive n bigger than 0. So it's just a von Neumann series, geometric series. And now you brutally pull in the LP norm everywhere. And the only thing you need is that the norm of this thing here is less than 1 in order for this to converge. So if you want this here in norm to be less than 1, you would, for example, want that the L infinity norm of mu times the LP norm of p is less than 1 by a completely trivial estimate. So, but what does that mean? So suppose you know that the LP norm of t is 1 over p minus 1. We're interested in ranges of p that are less than 2. Then the requirement on p becomes this one. So k, which is the L infinity norm of mu, times this thing is less than 1, or the exact range where we know that this thing self-improves. So it is a one-line, completely ridiculous triviality if you know this LP estimate. And it was a major conjecture before. So this is obviously not the proof, because no one knows the LP estimate of this operator. So this is supposed to motivate you. Now, to be honest, it's not really my motivation. So my motivation for doing these sharp estimates is, if you don't know the LP norm of an operator, means you have not really understood the operator. So a lot of those proofs to get sharp estimates are very structural. So it means you have to look at the operator just in the perfect way so that the proof should be easy, And it just didn't happen with this Beurling-Ahlfors for various reasons. And, well, so here is the real part. Now, here I'm not doing a very good job with definitions. On the very first slide, I had these operators, Riesz transforms, and we're going to define them again. So there are some other singular operators of convolution type where you can write the real part of these kinds of objects. And it's already known that the real part has norm p minus 1. So the upper estimate is due to Nazarov and Wohlberg, and the lower estimate is with like an adapted Bourgain construction by Geis, Montgomery, Smith, and Saxman with sort of a probabilistic argument a little bit. So essentially, a big chunk of that operator already has norm p minus 1. So some good news though. So the Hilbert transform, which is a very, very basic operator, which is convolution by 1 over x on the real line. And here we are looking at this operator on the disk. Its best estimates date back to the 70s. So they are much older than even the 2000 proof of the second order Riesz transforms. So let's go a little bit back and give you this example a little bit more clearly. So let's see what the Hilbert transform is for people who've really never done it. So L2 functions on the circle, think of writing them as polynomials in Z and Z bar. So that means you're taking e to the IKT, which is a Z on the torus, and you raise it to the power of k, and you're summing over all the k with their Fourier coefficients. So it's just a Fourier series of such a function. And these coefficients are the Fourier coefficients that can be done with this formula here. And Plancherel's theorem lets you write the L2 norm just like this. So now you realize that if you get rid of all the negative frequencies, you end up with an analytic function that is defined naturally on the disk. So all z bar derivatives are 0 because you just have essentially an infinite polynomial. And you also realize that the real part is u and the imaginary part is v. So essentially you take your original f, which is the full Fourier series, you double up the positive coefficients, you get rid of the negative coefficients. So basically what you've done, you've added this thing here. So what that means is that u plus iv will end up being analytic. And this is the Hilbert transform of u. So if you start out with a harmonic function and you want the the harmonic conjugate so that you build an analytic function, that's the Hilbert transform. Now the cool part is you don't have to go on the disk. You can also do this on the boundary of the disk by the means of a singular integral. So if you just know the boundary values, you integrate against the kernel, which is sort of a 2 pi periodic analog of 1 over x, and out comes this operator. So you can also look at analytic projections, and if you understand this one, you understand everything. You realize in Plancherel's inequality, in Plancherel's identity, if you just get rid of a bunch of terms, you realize that it's an L2 bounded operator. But you can also show in many different ways that it's bounded in LP, and that there exists a constant. That there exists such a constant CP. So now I'm going to show you how you can find the best one. It's not my proof, unfortunately. It's from the 70s, very beautiful. So the proof I will show you is from the 80s. So you want to know the CP. So here's the theorem by Pichorides. So he figured out exactly those constants. So f tilde is the conjugate function of f. And he managed to estimate the LP norm of the conjugate function precisely by the LP norm of the function itself, by these kinds of dependence on p and their optima. Now, and the proof is so great. I mean, it's really just complex analysis on the disk. So instead of really estimating this thing directly, you can also go ahead and estimate the analytic function f itself, and then there are tricks to go back to f tilde. So we will just find the best estimate for this green f, which is the analytic function. So, and we will do it for the range of p between 1 and 2. And suppose we have a miraculous function, capital G, which has the following nice properties. It is negative on the real line, it is superharmonic in the complex plane, and it has a strange inequality. Now, what's the motivation of this inequality? So the z is going to be the f, and the little x is going to be the little f. So you sort of want to estimate the big F by the little f with this norm thing Cp here, okay? So we want that this function actually dominates that. So it means we can control this. So let's see what this does if you have such a function. So now you plug in, you integrate over little pieces, little circles inside the disk, and you integrate over the angle, and you will find out that this thing here is less than all this. It's basically just this inequality here applied to special things plugged into this function. Now, if we could drop this term, we would be just done, because this is exactly the statement of the theorem. So why can you drop this term? Because you're composing a superharmonic function with an analytic function. Nice things happen. And you also have this control on on x, which are real. And here, this is a normalized analytic function, and you know that it's real. So you basically drop this term because it has the correct sign by the superharmonicity and the sign here, and that gives you the estimate. The trouble is you have to have such a function. So that's it. And if you stare at it for a while, you sort of see how it's built. So that's the Hilbert transform on the disk, and I'm much more interested in singular integrals in Rn or in other structures and more general situations. So this definition, so analyticity, it really works very well on the disk in some other situations, but singular integrals are much more general. So let's try to reinvent the Hilbert transform in the real line. So there are many ways to do this. Well, here's the convolution by 1 over x, and then any such convolution operator, if you take the Fourier transform formulae of the function 1 over x, you will end up with a signum function like this. So it has a Fourier multiplier that is -1 for that is I for negative frequencies and -I for positive frequencies. And you can also have this definition, this implicit definition through the Laplacian and the derivatives. And this is very useful if you want to go to more general settings. So if you're going to Rn, you basically reproduce this formula and you end up with the Riesz transforms. And this is basically the definition that's used everywhere on manifolds and groups everywhere. Now, I'm going to do something that I don't know how much probability you've had. So I will try to do my best. The Hilbert transform has many different phases, you know, and one of them, or the Riesz transforms have many different phases, and one of them is this incredibly beautiful probabilistic interpretation of the Riesz transforms that is due to Gundy and Varopoulos from the 70s, that I will try to sketch what it is. So, but you need to know what a stochastic integral is. So I don't know how much you've heard about this, but you certainly all know what a Lebesgue integral is. And then if you, or let's just start with a Riemann integral. And then if you, instead of differences from a Riemann sum, you put the differences of a function, that's a Stieltjes integral. And if you're doing a Stieltjes integral, it's pretty easy to see that the function that you're putting there, that's supposed to replace your measure, it should be really of finite variation for this to make any sense. And if you are trying to trace this, why you really need this finite variation, if you look at that, you realize the object that you're integrating, when it already sees what your function is doing, that is actually replacing the measure, you realize that it gets really messed up if the variation is not finite. But the function that you're integrating has to see what's happening. Now, if you want to not have bounded variation or finite variation, so for example, if you are having a Brownian path or something like this, it's not of bounded variation. Then you have to define integrals differently, and it's absolutely gorgeous. It's done by Ito, and you arrive at a stochastic integration. So the trick is to look what fails in the Stieltjes integral for lack of bounded variation, and you make sure that the object that you're integrating in some sense doesn't see the Brownian motion. So it's not very precise, but that's the idea. It's essentially, I mean, if you solve an analysis, it's not a big problem. It basically, you just read it. So how is this related to Riesz transforms? So this is all like Riemann integrals here. Okay, so if you, what is this? You apply the Riesz transform to a function f and you integrate it against g. So these brackets basically mean exactly this, rk of f g dx, where x is the variable in here and there. So there are about 5 different ways to see this. So you basically work either with the Fourier multiplier or with some semigroups. So, but there is a way to show that instead of applying the Riesz transform to the function f on the boundary, you can just go ahead and take a harmonic function of f and a harmonic extension of g, which is your test function, and then it will take a t derivative in that test function, and it will take a xk derivative in this u, and you integrate over one more variable by not forgetting the t here. So it's fairly elementary, but it's very nice. And why do we like it? Because it looks like the Riesz transform has disappeared. It hasn't. But the action of the Riesz transform has been replaced by this process. So basically, now I'm just going to write this as a full gradient, and I'm going to multiply it by a matrix A. It's got almost only zeros in it. Okay? So basically, A has almost nothing there, and it is a matrix of norm 1, and this is the full gradient. So it's also an orthogonal matrix. which is going to be interesting. So I'll go quick here because either you know this or you don't know it and you won't know it. So this is essentially the proof of Gundy-Varopoulos, and it's a fantastic exercise if you are in need of learning stochastic integration. So what you can do here is, remember this was basically just the Riesz transform paired of F paired with G. Those are the harmonic extensions. And now it is true that if you are having here a Brownian motion which is of the correct dimension, and you're plugging this into this object here, and you integrate with respect to ds, taking expectation, that gives you this back. Now, how do you see something like this? So there are many ways to see it. I mean, one of them is applying Ito's formula, and certainly those people who have done a lot of product martingales, they will see it immediately. So essentially what is nice is if you have a harmonic function, a lot of terms drop, and you get such integrals from such stochastic integrals that represent perfectly a martingale which represents your harmonic extension. So in order to go from here to there, you have two stochastic integrals. And this is not really a stochastic integral. You know, it's just an expectation over all these paths here. And then you continue with this expectation, and you're doing a lot of the same sorts of operations, and you end up with a Riemann integral again, where you're pairing something against G and you're just integrating. So before you had the Riesz transform of F here integrated against G, now you have this stochastic integral, where this expectation is conditioned by arrivals at W0, where W0 is a point on Rn. So you're having your functions on Rn, you're mapping it up to Rn plus 1 with harmonic extensions, you're having all these Brownian paths, and you're taking expectation of all of the ones that arrive at W0. And so essentially that's that formula. You have basically written your Riesz transform, at least in a weak form, as a stochastic integral. I mean, if you do the calculations, you would love it as much as I do, but it's not possible here. So, so what does this mean? It means this proof by Essen, what he did, there's a perfect library between subharmonic functions and martingales, or harmonic functions and martingales. It works perfectly, this library. And you can translate this proof of Essen into a stochastic setting. So that means that you're getting a very general estimate for orthogonal differentially subordinate martingales, which was done by Banuelos and Wang much later. So since very many operators of singular integral type can be represented through formulas similar to Gundy-Varopoulos by such stochastic integrals, you get the LP estimates for free. So this is more or less wonderful. So if you have there are singular integrals on one hand which are completely deterministic, and you have these stochastic processes and martingales on the other hand, and there's a duality between them. So, very specific duality. So now, the discrete Hilbert transform, why does it fail? I mean, you would expect that you just choose the correct kind of process that will model correctly this discrete Hilbert transform, and then out comes the LP estimate. And this works for some operators, but for the moment it does not work for the Hilbert transform. I mean, we know how to write such a formula, but we don't know how to recover the LP estimates. But before you're doing that, you should actually first agree what a discrete Hilbert transform is. So you could say, since the continuous one was convolution by 1 over x, we should do convolution by 1 over n. And we just throw out n equals 0. Now that's a really stupid way of doing it, but I think that's the classical one. But it has no good properties at all, so it's not really a good choice. Then you can say, my classical Hilbert transform had a very special Fourier multiplier that was composed of two pieces of constant functions. I'm going to do the same for the discrete case. So I will take a Fourier transform on Z, and I'm going to make sure I'll have a multiplier that is constant on the right of 0 and on the left of 0. I think that's right now the definition that's mostly accepted. And then you can say, I'm going to take the definition of the Riesz transform, and I'm going to do everything that I know how to do on R, I can also do it on Z. So it basically means you need to know what the Laplace is and you need to know what the derivative is. So here's a function that goes from Z to R, okay? So here is Z and here is R. So it's 0 almost everywhere and it's 1 here. So now if you're going to take a derivative, you can do this in two different ways. You are assigning to this value here the difference between those two, which is 1. And you're assigning here the difference of those two, which is -1. But you've made a choice. You've made a choice to go this way. You could have also gone the other way. So there are two choices with Hilbert transform if you're doing it this way. One of them is going to be a H+, the other one is a H-. But if you're taking the Laplace, you're going to make sure that you want to be as centered as possible. So you'll take a D+ and a D-. And then when you're doing this, it's not very meaningful on Z, but on Z2, if you're doing this, what it turns out to be, you're comparing all the values around the point with the point in the center. So it's exactly a Laplace. So when you have all these structures, then you can define your discrete Hilbert transform this way, and it's always a different operator. So, and with this definition, you can do whatever you want. So you can do it, those derivatives, they clearly exist as partial derivatives if you have products of sets. So for example, if you have a bunch of Lie groups and if you have a bunch of copies of Z, you can also write down what your derivatives are, and you can write down what the Laplace is. So I promised Lie groups in my title, and I hope that I'm not going to disappoint everyone who does Lie groups. There's nothing really deep here. So the only thing about Lie group that is really important here is that it is, what's special here is that it's a non-connected Lie group. So for example, take a very, very simple Lie group S cross S and align 3 of them in a circle of 3 points. So that is not connected. You have S cross Z mod 3Z. So that is also a Lie group, a very simple one. But for analysis purpose here, for controlling of those things, what's very difficult to control is if it's not just one object. So the Lie group doesn't have to be commutative, but we need this compactness criterion, so compact Lie group for the connected part in order to make things work. This is because there's this nice bi-invariant metric. So you can just run all these definitions for those objects. So here are the discrete derivatives, partials, and the continuous first derivative. You write it like this in the Lie group setting, and here you can also write it like this as operators. And then you can define your discrete part of the Laplace and your continuous part of the Laplace, and you can define your Riesz transform for the continuous Lie group part. And here you have plus and minus choices as soon as it's discrete. So those are all the Riesz transforms you can get in different directions. So now if we are chasing after sharp LP estimates, so I've shown you the proof for the Hilbert transform on the disk on the real line. And then the Riesz transform also follows. There are several different proofs, and one of them follows from the martingale interpretation. And then the second order Riesz transform in the Euclidean space is due to Nazarov and Wohlberg. And then this is our contribution, that the second order Riesz transforms, it's surprising, but here you can really do the discrete optimal estimate. So for the Hilbert transform, it's a super, super famous problem. And for the second order Riesz transform, it's really much easier. Okay, so we could get this one, and it's really, it was very surprising to a lot of people that it actually could be done. So, and you know, we have two different proofs. So one of them is with one of my collaborators from 2014, which is a deterministic argument. And now we have a new proof, which is probabilistic, and while we were at it, we included the Lie groups. So the probabilistic proof has the advantage that you have to go through such a beautiful formula like Gundy-Varopoulos type with a specific process. So you're not going to do just Brownian motion here, because the Brownian motion that you have running in, for example, in the upper half space, it doesn't work here because you have your Lie group here, and you have 3 copies of random parameters. You have you have a Brownian motion for each generator here, and you have something else to get from one to the next. So you're doing a Brownian motion here in two directions, and then while you're doing that, you have a randomized clock here that at some point will tick, and when it ticks, you will jump to the next. So that will give you a process that walks here. When it ticks, you jump, and then the clock starts over, and at some random moment it ticks again, and you jump again. So that is the process that we use in order to get such formulas. So why is the Hilbert transform so different from the second-order Riesz transforms? So because as a probabilistic object, it's a completely different thing. So the periodic Hilbert transform, or operators like it, like the Riesz transform, they are dual to martingales that are differentially subordinate, whatever that means, that you can control increments, and orthogonal. So orthogonal should remind you of Cauchy-Riemann relations. Okay? So, and differentially subordinate is a property that all of them sort of have. So if you want to control the Hilbert transform, it's dual to differentially subordinate orthogonal martingales. If you want to control squares of Riesz transforms, you drop the orthogonality and you just have differential subordination. So this also explains why the norm of the second-order Riesz transform is a little bit bigger than that of the Hilbert transform, because you have a more general martingale. You dropped something. So now what's interesting, this proof by Pichorides of the periodic Hilbert transform, it was first, and then it was recognized that it had this sibling in the probabilistic world, and they could inherit those estimates. However, for the second-order Riesz, it was the other way around. So there are very famous theorems from the 80s from Burkholder that estimate exactly such martingales, and then it was actually noted by Wohlberg and me in a different setting that this is really extremely dual to these differentially subordinate martingales in a very direct way. So, and essentially, you have seen this Essen function that does this, and Burkholder, in his probabilistic proof, he also has a very magic function that will give you exactly those estimates. All right, here's our theorem stated neatly. Not really that neatly. So you have these second-order Riesz transforms, and you go from LPG to LPG, where this is like the discrete part. Here it's Z over 3Z, and the continuous part, which is S2 here. And you have those estimates not just for one of those second-order Riesz transforms, but pretty much for any kind of combination. And it's more general than that, but it's not really, let's not worry about it. So such things are included and a few more. So while as we cannot even estimate the first-order Riesz transform in an optimal way on anything discrete, we can estimate all this stuff when it's a second order. And it's p minus 1, doesn't grow with dimension, nothing. And the Hilbert transform does not work. It's just an operator on Z. So it's kind of remarkable. So, and it's optimal. Well, it's optimal as soon as you have a difference like this and of two infinite components. So one of my co-authors is a numeric analyst. So, and this is sort of how we found these problems. Because what they care about is discretizations of things. So if you discretize the real line into points here, you discretize the information of a function. Okay, and if you have this delta x going to 0, you basically recover your function f. The same thing on the disk. So if you're estimating these Riesz transforms on these grids, it is called a finite difference scheme. So such a scheme means that some derivatives will approximate the continuous derivatives, and the approximations of the function will approximate f. So what does this mean? Our discrete estimates, let's say just on Zn, they will recover the estimates in Rn, but not the other way around. So discrete estimates are always more difficult, and it almost never happens that you have in a discretization the exact same control as you do in the continuous setting. So basically ours gives the continuous case back, but not the other way around. However, sharpness for the continuous case gives us sharpness for free. So there's that. Now, we have 2 papers on this. So the first one is with my first collaborator, Domé-Levaux. It's a deterministic proof where we use Bellman functions. And the new probabilistic argument from this year is with Nicolas Arcosi and Komla Domé-Levaux. So the probabilistic proof, it develops such a Gundy-Varopoulos formula with this kind of process. And it has the advantage that you get a whole lot of other theorems for free. So everything that's known for certain martingales with differential subordination, you get it for these second-order Riesz. For these second-order Riesz transforms, we had a lot of sums of those, very many of them, and it was still just p minus 1. So even if the dimension grew and very many of them grow, you still have the same estimate, which is free of dimension. Now, if you go back to first-order Riesz transforms, what you generally measure is the Riesz vector, which means that you apply each Riesz transform to F, you square everyone, and take the square root. So you take the little L2 norm of the Riesz vector. And then you try to estimate the LP norm of that. So that goes pretty well in very many different ways. So in Rn, there are many different proofs. And I think I'm not putting the first proof. I think from this Gundy-Varopoulos, you get also a dimension-free proof. So there are many different dimension-free proofs. In the Gaussian setting, you can do this. On the Heisenberg group, on certain Riemannian manifolds, even if you have drifts in the Riesz transform, you can still get dimension-free estimates. So, but what do all of these spaces have in common? They have continuous derivatives. So all these spaces are continuous, no jumps like this. And that's why they're lucky. So this woman has a fantastic result from 2004. And what did she prove? She showed that in Zn, there is a dimension-free behavior of this little L2 norm of all the Riesz transforms when p is bigger than 2, and there is a dimensional growth when p is small. Now that's really strange. I mean, you can do Heisenberg group, but you can't do Zn. So her positive result are non-commutative methods. Now, I didn't understand the word, but she explained it to me, and now it's okay. So it's a fantastic proof with where she embeds these discrete derivatives in a very large space that acts more like a continuous space, and on the way there is something used that's really specific to large P. And the negative result is a counterexample. So there was such a counterexample for Z2, where it's already growing with dimension. And this counterexample could be modified, and I want to show you just the punchline of that example. So it's a lot of writing, and you don't have to read it, I promise. So what's important here? Let's look at those discrete derivatives. There is something happening that never happens in the continuous world. So if you take the derivative from here to there, notice that the support of this function is just this one point. But the support of this function is 2 points. So in particular, this point here is in the support of the derivative, but it's not in the support of f. That's never going to happen if you're in the continuous setting. And this is what makes the counterexample work. Now I promised you to only show you the punchline. So Riesz transforms in LP means estimates like this. Here's the derivative, and here's the Laplace. Okay? So now you want to build an example of functions that are going to look like products of those things here. Very, very easy products in such an easy way that you can just explicitly calculate everything and calculate easily those LP norms and so on. So, and then when you do all this calculation, you're going to have d plus of f here, and this is the support of f. Now that is the complement of the support of f. So if you were in a reasonable space, that would just be 0, because you're multiplying the complement of the support of f with its derivative. But since you are in this situation here, it's not 0. And for this particular example, it really isn't 0. So, and see what you get when your p is small. You're getting this p's root of n here, and here you're getting just square root of n. So it's never going to happen that this is independent of n, just because of these strange support properties of the discrete derivatives. That's all I have to say.
Thank you. Do we have any questions or comments?
Okay, since the P norms and the Riesz and Hilbert transform are the same, does that suggest that the P norms and the discrete Hilbert and discrete Riesz transforms can be the same as well?
The problem is the same difficulty. I mean, if you're going after these stochastic proofs, there's no difference.
Okay.
So yeah, I mean.
I can understand that a probabilistic method can yield a bound on the constants. This is sort of always a reasonable thing. To have the best constant means that the extremals are somehow low dimensional. I mean, that the extremal ones actually come from the function context and not the functions on paths context. Is there an easy way to understand why that's true? Why is the probabilistic method yielding the best constants as opposed to just constants?
It's not that the probabilistic method leads the best constant. There's really a duality. You can absolutely use the probabilistic proof and remove all probabilities, and you'll get these proofs. So I mean, for the Hilbert transform, there was no probability, and I'm pretty sure Pichorides doesn't know any probability. And if you do have the Burkholder's theorems, which are stated in a probabilistic way, but you know, if you reduce them to a dyadic situation where you just basically all your arriving paths somewhere, there's just one, you know, and there's no probability really. So it's not really only so probabilistic. It's another way of doing it, and it's a very elegant way. However, since you're asking about the extremizers, you know, that shows that this is optimal, those are kind of constructions by Bourgain that have been developed for other things, and there you see very well that there is a flow there. So I don't know if I answered your question, but...
Yeah, I had a very similar question. So this Pichorides argument cannot be interpreted probabilistically?
It is exactly, you can interpret it as a library. So there's a harmonic function becomes a martingale, you know, and subharmonic, submartingale, superharmonic, supermartingale. So essentially, if you take a function f and then you take the Poisson extension, and then you have this process that for every time for every time t, you take the Poisson extension at that time of your g, that gives you a martingale. So you can write it with a stochastic integration. And with these kinds of methods, you probably see a duality rather quickly between those two things. And it's been done in the 90s, not any earlier.
Okay, any more? If not, well, thanks very much, Stefanie, for a great talk.